Welcome back, focused learners. Today, we're doing something pretty incredible. We're actually pulling back the curtain on the magic trick that is modern artificial intelligence. We're going to uncover the 2026 engineering cheat codes behind those mind-bending AI audio tools you've been hearing literally everywhere. Systems like Suno, 11 Labs, and GPT-4o. If you've ever wondered how a machine can seemingly synthesize human emotion, breath, or a full orchestral track completely out of thin air, well, you are in the exact right place for this explainer.
Okay, let's dive right into this. Here is our roadmap for today. 1. The audio data problem. 2. Neural codecs. 3. Two paths to generation. 4. The streaming constraint. 5. Pitfalls and challenges. And finally, 6. The 2026 production landscape.
All right, kicking things off with Section 1, the audio data problem, specifically magnitude scaling. So before we can even talk about generating anything, we really have to wrap our heads around the sheer, overwhelming size of the canvas we're asking these AI models to paint on. We're dealing with a massive mathematical hurdle right out of the gate. To put this into perspective, just ask yourself this. How exactly does an AI listen to 240,000 individual samples of audio? Because, a mere 5-second audio clip at a standard 48 kilohertz sample rate, that is an impossibly dense, one-dimensional signal. If you tried to feed that raw sequence into a standard transformer model to process sequentially, well, the compute requirements would literally melt your servers instantly. So how on earth does the model actually handle all that data? Well, spoiler alert, it doesn't. It just doesn't. And that's kind of the grand illusion here. Absolutely no production model in 2026 is actually looking at that raw, massive sequence of hundreds of thousands of individual audio samples directly. It's just computationally impossible to do efficiently at scale. Instead of drowning in all those samples, the industry standard is to scale things way down to a highly compressed token rate, which is usually right around 50 to 75 hertz. It's like, imagine taking a massive, dense, high-resolution flipbook and just boiling the whole thing down to only the essential keyframes, right? By stepping down to 75 hertz, the AI only has to look at 75 chunks of information for every single second of audio. But that raises a huge question. How do we squish all that incredibly rich sonic detail into such a tiny footprint without it just sounding like total garbage? Which brings us perfectly to Section 2, Neural Codecs, or as I like to call them, the ultimate cheat code. So every single major production audio model out there totally relies on neural codecs to bridge the gap between those messy audio waveforms and structured machine logic. A neural codec, and we're talking about systems like Meta's Encode, Google's SoundStream, or the big open source favorite right now, DAC, is essentially an encoder and decoder system. It uses a convolutional encoder to compress those raw, high-fidelity waveforms into a much, much slower stream of discrete tokens. Just like a large language model uses text tokens to represent syllables or words, a neural codec creates an acoustic vocabulary. It totally bridges that data density gap. So the really crucial point here is exactly how it builds that vocabulary. It uses a little something called RVQ, which stands for residual vector quantization. Now, hey, don't let the jargon scare you off. Imagine you're trying to describe a really complex paint color to someone. The first layer gives you the broad stroke. Say, okay, it's blue. But, that's not totally accurate. There's a margin of error there. So the second layer models that leftover error and says, all right, add a bit of green. Then the third layer refines the leftover error of the second and says, add a tiny drop of gray. It's basically a cascade of quantizers where each layer models the residual error of the layer right before it. And they all stack up to create a highly accurate but super manageable codebook index of sound. All right, moving right along to Section 3, two paths to generation, looking at autoregressive versus diffusion. Now that we've successfully crushed our audio into these neat, discrete tokens using our codec, we have to actually generate new ones. And in 2026, the industry is basically split into two very distinct generative paradigms. We essentially have two totally different brains for audio generation. Over on the left, we've got the token autoregressive approach. Think of this one kind of like a typewriter. It predicts the very next token in a sequence based strictly on the previous ones. It's naturally causal, meaning it moves chronologically forward, step by step, which makes it absolutely incredible for real-time streaming. It completely dominates speech tasks, like Microsoft's Volley. But then on the right side, we have latent diffusion, or its newer, sleeker evolution, flow matching. For this one, think of a sculptor working a big block of clay. It looks at the continuous latents all at once, kind of refining the noise into a clear, clean signal. This gives you faster inference and honestly much cleaner samples overall, which is exactly why it's winning the race for complex music generation. Think of tools like Stable Audio 2.5. To really grasp how beautifully elegant the autoregressive path is, let's actually look at the pipeline to build a tiny version of one of these. It's honestly like following a recipe. Step 1, you generate sequences of synthetic audio tokens. Step 2, you train a tiny token predictor on those exact sequences using standard cross-entropy. You're basically teaching it the core patterns of your new acoustic vocabulary. And step 3, you sample conditionally. You just give it a starting token and a style prompt, and boom, it starts predicting the next token from the distribution it just learned. It is genuinely remarkable how this abstract math translates into such a clear step-by-step recipe for making sound.
Okay, on to section 4, the streaming constraint, or the physics of listening.
Because here's the thing, having a great recipe doesn't mean the restaurant can actually get the food to your table fast enough. We have to completely shift our paradigm from just looking at audio quality to looking at the strict, totally unforgiving physical constraints of time. Now, what's really interesting about this slide is the sheer speed of this number, roughly 200 milliseconds. That is the latency of OpenAI's GPT-4o audio model. Since it's an end-to-end multimodal autoregressive model, it predicts and streams those audio tokens practically as fast as you can speak to it. For live, back-and-forth conversations, that blazing speed is just non-negotiable. But actually, contrast that blazing speed with this number right here, roughly 30 seconds. That is the latency you're going to experience when waiting for a system like Suno V4 to render a full song for you. Generating heavy, structurally complex musical outputs requires a massive computational cost. You aren't streaming this in real time while you chat. You're essentially waiting for this whole intricate tapestry to be woven together completely before you can even press play. Which brings us to what is essentially a fundamental law of AI audio. TPOT matters. Time per output token. You see, listening is physically bound by time in a way that reading text simply isn't. I mean, you can read a paragraph instantly if an LLM spits it all out at once, but you absolutely must consume audio chronologically. If your neural codec tokenizes audio at 75 tokens per second, while your server absolutely must generate at least 75 tokens per second to keep up. If it dips below that speed, even for a moment, the audio skips, it buffers, and that magical illusion of real-time generation is just completely shattered. Let's head into section 5, pitfalls and challenges. Time for a quick reality check. As absolutely magical as these systems seem, they are operating right at the bleeding edge of physics and computation. So let's impartially map out the very real hurdles they're facing right now. First off, codec quality strictly caps your maximum fidelity. If your codec can't compress a sound cleanly, the AI generator simply cannot fix it later. Second, remember those RVQ layers we talked about? Well, errors in layer 1 cascade and accumulate all the way down the chain. Third, maintaining long-term musical structure over thousands and thousands of tokens is incredibly hard. It requires these really complex sliding windows and crossfading, which directly leads to our fourth issue, nasty audio artifacts right at the clip boundaries. And beyond just the code, there's the data. These models have an absolutely insatiable appetite for clean, structured data. We're talking tens of thousands of hours of audio. This incredible data demand is the structural reason behind industry events, like the 2024 RAIA lawsuits regarding music ingestion. And finally, on the speech side, the simple fact that models can clone a human voice from a mere 3-second sample makes robust abuse detection and secure opt-out lists an absolute mandatory requirement for any responsible production deployment. And that brings us to Section 6, the 2026 production landscape. Let's map out the market. So taking all of that into account, the math, the codecs, the physics, the hurdles, let's bring these abstract concepts into the tangible landscape of the actual tools digital creators are using right now. And this brilliantly illustrates how different architectures perfectly serve very different use cases. Look at text-to-speech. 11 Labs v3 uses token autoregressive to hit a snappy 300 millisecond latency. GPT-4o uses multimodal AR to push that even faster, down to 200 milliseconds. But then look at Stable Audio 2.5. Tasked with high-fidelity music and sound effects, it uses flow matching. The trade-off there, it takes about 10 seconds to render just a minute of audio. And then Music Gen, depending on how you configure it, leverages token AR to try and bridge that gap for real-time music generation. So your 2026 cheat sheet is remarkably simple. Are you building a live voice agent for customer service or chat? You literally must choose Codec Autoregressive. Flow matching simply cannot stream trivially because it completely relies on that sliding window chunking, which just adds way too much latency overhead. But what if you're rendering a full 30-second music clip where the user hits submit and fully expects to wait a bit? In that case, flow matching wins on quality and total output fidelity, hands down every single time. It really all comes back to this one fundamental truth from the engineering source notes. Audio is the one output modality users expect to arrive as it is generated, not all at once. You can hand someone a fully generated text essay instantly, but you can't hand someone an instant 3-minute song without fundamentally changing how they experience it. Literally, the entire engineering stack we've explored today exists just to respect that single, basic human expectation. Which leaves us at a pretty fascinating crossroads. We have compressed the data, we've trained transformers to predict audio tokens, and we are constantly racing against the absolute clock of human perception. But as generative AI hits the physical limits of real-time streaming and raw computation, you've got to wonder, will we eventually invent a completely new mathematical framework to process time itself, or are our machines forever bound by the inescapable speed of sound? It's definitely something to think about until our next explainer. Thank you so much for joining us. Keep learning, and as always, keep asking great questions.